In the last video, we saw how diffusion was the driving force behind mixing at the molecular level, but how turbulent phenomena helped by firstly allowing a larger surface contact area between the air and the fuel, secondly by facilitating a greater concentration gradient, which speeds up diffusion, and thirdly by allowing more time for mixing, since the fuel and the air are bulk mixed. An analysis of this from a theoretical point of view is quite involved. However, you can find it in the Hypersonic Airbreathing Propulsion book on page 287 to 305. A simple theoretical treatment indicates that turbulent flow improves mixing by 20 to 30 times. However, as we'll see, there are various practical and second order limitations which reduce this to more like an order of magnitude, that is around 10 times. And this seems to agree quite well with most of the measured figures which are available. One issue in particular is a problem. We've already seen in earlier videos how shock waves form. When fast flows hit obstacles, their component molecules don't have time to rearrange themselves and get out of the way. And so they end up forming a thin, hot, dense layer. Well, exactly the same thing happens if the fuel and the air are not moving at the same speed and they collide with each other. And as a result, the region of compression this time is a barrier to mixing because the air and fuel molecules find it difficult to cross this ultra-dense region. Indeed, long before an actual shockwave forms, the mixing layer size drops. The reasons for this aren't immediately obvious, but they might be because of lower size density increases or due to the relative velocity of the molecules as shown in the drawing. A number of authors have done studies into this phenomenon, and perhaps Slessor is the most comprehensive. A graph produced from his survey is shown in the diagram. Here we can see that the mixing layer thickness starts to drop off almost immediately as the fuel and air move at different speeds. And by the time that the difference is max 0.2, the layer is only 0.8 of what it would have been had both components been moving at the same speed. At very large speed differences, it tends to only 1/5 of its original value. And so this presents something of a dilemma, because to induce turbulence and ensure good bulk mixing quickly, we need a difference between air and fuel velocities. But this itself causes the issues with compressibility problems which we've just been describing. As stated previously, the measured figures seem to show that good turbulent mixing is around 10 times better than the plain simple diffusion alone. So let's look at what the actual figures for mixing look like. The diagram below shows the mixing layer thicknesses in an engine at different Mach numbers. This is based on a famous design by Billig, which is a very typical published scramjet design. I'll include a reference to this and also some other useful standard figures in the video description below. Now remember that well-designed turbulent mixing can improve this figure by a factor of about 10, even including the compressibility effects. We can see therefore that using either injectors or some other way of placing the fuel, we still need to bring it into contact throughout the mixing volume within a few tens of millimeters for it to be fully and effectively mixed. This goes some way to explaining the lack of success of simple wall-mounted injectors. So let's have a look at two types which are very often used. The first is a normal injector. These inject fuel at right angles to the flow, as shown in the diagram. Since the fuel speed here is 0 compared with the air in the direction of the duct, we would expect, and we would find, very low mixing in the initial contact area. As the fuel moves further down the duct, however, its speed increases and the situation improves. A second type of common injector are ramp injectors. These are designed to inject the fuel in the direction of the airstream and therefore lessen the strength of the interface shock wave between the fuel and the air. There are two basic configurations of these, which are shown in the diagram. Generally speaking, the expansion type seems to show better performance. Of course, there's a compromise here. The faster the fuel is injected, the smaller is the compressibility problem, but the further the fuel moves down the duct before mixing. The top of these injectors is often profiled to encourage turbulent mixing. In this case, encouraging the formation of vortices at the edges, which act like the instability discussed earlier. Other projections into the duct can also generate similar results. It should be obvious from this discussion that simple devices like the one shown above would have difficulty producing the necessary air-fuel contact. So we need to look at some other techniques, which we'll discuss in the next video.